Okay, welcome to the close of chapter 4 of the Introduction to Machine Learning course. This is the topic of linear classification, which we are wrapping up. Our last lecture was about iterative re-weighted least squares, or IRLS, which was based on the second derivative. Hope you found that interesting. And I understand that your breakout session is going to deal with IRLS, that method. So today I will pick up on the last topic in this linear classification methods, the probabilistic discriminative methods. And this topic is Bayesian logistic regression. Okay, it's a somewhat complicated topic, but it is nice to have it under your wings that you have covered this. Some of it may not be to your liking, but it is a very interesting topic for those of you who are mathematically inclined. I'll try and make the mathematics as palatable as possible. It involves using the Bayes rule, priors and posteriors, and multiplying priors with likelihoods to get posteriors. So it involves repeated application of the sum rule and product rule of probability, which is in the continuous form. They become integrals. And so these kinds of equations and all we'll look at. Ultimately, they're also fairly straightforward. So that's the topic today. So there is a number of things we'd like to cover as pieces here. We begin with a topic called Laplace approximation to a probability distribution. But to keep in mind that machine learning is really, in some sense, applied statistics. So it's figuring out probability distributions of the data. And from that, it is making predictions. And so when you're dealing with probability distributions, you can actually estimate the distributions exactly from just the data. That's called the frequentist approach. The other approach is, well, I don't have that much of data, so I will assume there is a distribution underlying the data, but I don't know the parameters. Like I don't know the mean, I don't know the covariance matrix, but I know it's Gaussian. So in which case you can have a prior distribution over the parameters saying, okay, most likely the value is this, but there is also an uncertainty associated with it. So that's called as a prior distribution over the parameters. So that approach is powerful when you don't have lots of data and mathematically intriguing. So that's the topic for today. So the kinds of things we want to do is how do you approximate a probability distribution? And that is can be done with approximating a distribution with a Gaussian is the topic. And how could you, what kind of Gaussians would approximate your data? So one approach is called the Laplacian approach. The Laplacian is saying, okay, for your data, is there a mode? Mode means at some value, it is taking a peak, this probability distribution. That's called the mode. For a normal distribution, the mode is the mean. At the mean of the distribution, we're going to have a peak there. So, but in another distribution, the mode may not be the mean, but there is some peak where it gets the maximum value. That's called the mode. So the Laplacian method says you could approximate your distribution by centering a Gaussian whose mean is at the mode of the distribution you're dealing with. So this is to find a Gaussian distribution for the distribution at hand. Another approach is also to find a Gaussian, but not necessarily centering it at the peak, but finding the best match. It means the two distributions should have a lot of overlap. And that approach is called a variational approach. All right, it's based on variational calculus. So we'll look at both of these approaches to approximate probability distributions. Now, why do we need to approximate probability distribution is a question. In linear regression, we'll start with linear regression and how do we use a Bayesian approach to linear regression. The Bayesian approach says there isn't an exact answer to what you're asking. There's only a distribution as the answer, right? So there can be any of these values, the answer you're looking for. It's called the predictive distribution. For this input, what should be the output? That's the kind of prediction we're making. But we're saying, not necessarily give an exact answer, but a probability distribution as the answer. That's the Bayesian viewpoint. And in linear regression, it turns out that posterior distribution that you're looking for, posterior is a combination of the prior. To begin with, you say there's a distribution that I think it exists. And when the data modifies it, you get a posterior out of it. And it turns out that the posterior distribution times the conditional distribution that is needed for the prediction turns out to have a nice integration that happens when you're assuming, let's say, a Gaussian prior on the parameters. And you get a nice closed form solution for that in the linear regression case, even for the Bayesian case. For logistic regression, that is not the case. So we look for approximations because we end up with a distribution that is posterior distribution that is this sigmoid, okay, which doesn't multiply nicely with a Gaussian to give another Gaussian. So you need to replace that with a Gaussian to get a better approximation. So all these little intricacies of so we're gonna delve into Bayes rule, conditional distributions, some rule of probability, product rule of probability, um, and Laplace approximation, and variational approximation, all of which kind of come into play here. And these topics are not necessary only for this simple linear classification problem. They occur again and again. They occur in deep learning as well. So you might as well pay attention to it while we are discussing it in a simpler setting, which is the simpler setting. This is where you get the concepts, or at least you know where the concept exists. When you go on to study more complex models and say, oh, that's variational autoencoder, and what does variational mean? All right, so you need to come back to the basics and look at it. Okay, so we are getting into this exploration, a difficult terrain, right? It's like somebody setting out to climb a very complicated thing, a mountain, right? You're wanting to climb a mountain because the mountain is hard to climb. You're trying to climb Mount Everest or Mount McKinley, which is very hard. You have to determine to yourself that I'm going to do it. Throughout the path, you encounter obstacles and you have to overcome it, saying there is some pleasure and joy to reach the top. Say, oh, I get it now. So after the effort, but you can't get it without you can't drop yourself on a helicopter and to the top of the Everest, right? I mean, you could do that, I suppose, but all the joy in it is gone, and what have you learned in the process? So we're gonna go through this, and so you got to be with me as we climb this mountain of Bayesian approach to even the simple problem of linear regression, logistic regression. Okay, so let's begin with Laplace approximation first. That's the order in which chapter 4 is arranged. Although Laplace comes in a bit later, but let's do that first. Let's see. I'm going to share screen. Hopefully it works. 4.4 Laplace, okay. Share. Okay, Laplace approximation. All right, hopefully you can see the slides here of a pure mathematical topic called Laplace approximation. And this is going to be, so you have to motivate yourself. Why do I need Laplace approximation? You're going to need this when we do Bayesian logistic regression. All right, that's where it's going to get used. So we'll first see what is a Laplace approximation. So this is chapter subtopic Laplace approximation in topics of, we're still in linear models for classification. We did discriminant functions, probabilistic generative models, probabilistic discriminative models. Probabilistic discriminative models were a very big topic where we studied not only logistic regression, we also studied IRLS. So today we are into Laplace approximation, and hopefully, and yeah, we will cover Bayesian logistic regression as well. So topics in Laplace approximation. So what are we going to learn in this particular segment is, first of all, why do we want to look at Laplace approximation? And we will look at finding a Gaussian approximation in the one-dimensional case. Okay, I've given you one-dimensional probability distribution that is something is not Gaussian, but Laplace approximation says, I'll find you a Gaussian as near that as possible. And then we'll say that can be generalized to m-dimensional space. So we can say not just one feature, but m dimensions. We have m feature vectors, right? And then we'll also talk about the weakness of the Laplace approximation. And there is an important topic hidden in the bottom of this called model comparison using BIC. You might have heard of BIC, right? It's called the Bayes information criterion. Other than about Laplacian, that concept is an extremely useful concept. Particularly in unsupervised learning, BIC is important. I believe in project number 2, you're doing both supervised and unsupervised learning. And yeah, you're doing autoencoder, I suppose. Another famous, the most famous unsupervised learning task is clustering. I give you a bunch of data and please tell me how many clusters are there in this data, and what are the clusters? What are the data points that cluster in one group, another group, and so on? And how do you compare a clustering with 3 clusters, 4 clusters, 5 clusters, 6 clusters? So that's called model comparison. One model says there are 3 clusters, another one says there are 4 clusters, another one says 5 clusters, 6 clusters. So what is the criterion? How do you measure goodness of the, so that is called model comparison. So we kind of launch it from Laplace approximation into some criterion for model comparison using BIC. So this is all hidden when we learn this topic. So first of all, what is Laplace approximation? The Laplace approximation framework aims to find a Gaussian approximation to a continuous distribution. So it's a one-dimensional case. The input distribution is this green mountain over here. It's not quite Gaussian, right? It's kind of goes very quickly, goes up very quickly, and then slowly comes down. And we're saying we don't want to deal with this more complicated distribution. Can you just give me a Gaussian that approximates it closely? Laplace says, tell me what is the mode of this distribution. Where does it peak? It says, okay, this is going from -1 to 2. And at 0.44, there's a peak. That's where this green mountain has a peak. Then Laplace says, I will find you a Gaussian that is exactly with mean 0.444, normal with, oh, no, I'm sorry, this is 0.22. I wrote it wrong here. This would be 0.22, 0.44 is actually the standard deviation or variance. Should have been 0.22. Okay, there's 0.22 here rather than 0.44. And so we find a normal distribution over here. And so the only thing it is doing is it has got it's got its mean there, and I guess we need to specify its spread also somehow. Whereas another more sophisticated approach we'll look at later is the variational approach, which is also finding a Gaussian, but this Gaussian is not centered at the mode. It is centered anywhere, but it is trying to find a Gaussian that overlaps this green as much as possible. So you can see this blue curve here has more of an overlap with the green than the black curve here, which is less of an overlap. The amount that is like the white region here is bigger than the white region over here. So these are the kinds. So this is what we're trying to do. So how do you figure out this Gaussian? Laplace, we're only first going to look at Laplacian. In the two-dimensional case, where you have two variables rather than one input variable, the distribution is going to be a Gaussian hill superimposed on these two dimensions. And these are all contours of constant density. The black here is one of them. And then there is the true one is in this light color here. There's a light colored lines here. And the Laplacian is a true Gaussian. So it is trying to find it. But the modes of the two are coinciding. So both of them are peaked at this point. So the modes are coinciding, but the spread of the distributions are different. So Laplace tries to find that. So what does it take to find the Laplacian? This gets a little complicated, but don't get too lost here. But keep in mind what we're trying to do. We're trying to just find a Gaussian with modes that are the same. And then we have to think about how do we fix its standard deviation also. So why study Laplace approximation? We shall discuss Bayesian treatment of logistic regression. It is more complex than Bayesian treatment of linear regression. In particular, we cannot integrate exactly because of the nature of the sigmoid function that is involved in logistic regression. We cannot integrate exactly. In machine learning, we need to predict a distribution of the output that may involve integration. So why do we need to do integration? Is because it is not enough to say, look, I have learned, I started with a prior distribution of the parameters, and then I now have a posterior distribution of the parameters after observing the data. But what are you going to do with the posterior distribution of the parameters is you need to now perform an integration over the distribution of the output condition on the parameters. And that integration, or the summation if you are dealing with a discrete case, gives you the prediction saying what is the value of the output, what is the distribution of the value of the output. So we begin here by looking at the case of Bayesian linear regression. So how does one get output in linear regression using the Bayesian approach? So in the Bayesian approach, we have a prior distribution P of W. W is a set of weights. We obtain a posterior distributions W given T, or W given the data. And so we convert PW to PW given T. But the prediction, the output T you're going to get, P of T, T is the output, the target output, is obtained from a joint distribution of T and W. W is the weights that you have in your model. That's a joint distribution of P, T, and W. And because your model has these parameters in it, so we are working with not only the output, but also all the parameters. So by the sum rule of probability, you can obtain the marginal PT out of the joint PTW by summing out the variable which is there that you don't want. So integrate it over all values of W, which is shown as PTW dW. Now this PTW can be written by using the product rule of probability, which says PTW can be written as PT given W times PW. That is simple application of product rule of probability. Now, frequently we kind of end up conditioning things. If this formula holds, then if I say PT given some set of things, that that are conditioned upon. If you condition everything here by the same things, then that still holds. So we can say the probability of the target given all the vector of all the possible outputs and some parameters alpha and beta. These alpha and beta are hyperparameters that are going to come along with us. And we'll see what these are. One of them has to do with the noise model in regression that you're dealing with. That's the beta parameter. That's the variance of the noise model in regression. And alpha has to do with a hyperparameter associated with the prior of W. So in the Bayesian approach, we take the stand that PW, you see this box here, PW. So it's a prior distribution over the parameters W. So the weights are not like you don't know anything about the weights. You're saying I have a prior distribution. And what is that? It's a normal distribution with, no, it's a normally distributed weights and with a mean M naught and a covariance matrix S naught. And what is that S naught? Is some alpha inverse I, which means it's an identity matrix whose diagonals are all this alpha inverses, right? So it's specifying the prior distribution also as a Gaussian with a very simple covariance matrix, right? So we say the weights have a prior PW. This PW has a prior. So it's possible to plug this PW in right there and integrate it out, or it will give you PT. Or if you have converted this PW into a posterior PW given tau, given T, this is before you observe the data, this is after you observe the data. Well, if you're making these assumptions of Gaussian prior, the posterior also turns out to be Gaussian, mathematically showable that this is also going to be Gaussian. And so we can plug in, this PW is going to be either PW or PW given T. PW is Gaussian, PWT is given T is also Gaussian, except its parameters are going to be different. Mn is based on the data set. Mn is based on the data set. It's got all these terms, the design matrix coming into play here. And Sn inverse similar to S naught, and that's also coming into play, and the design matrix coming into play, and so on. So we're going to have PW is going to be playing a role, the prior and the posterior. And what about this first part, T given W, which has become T given W comma beta? We are conditioning upon some things. We are leaving out things it doesn't depend on. PT given W is coming from here. We're conditioning upon things that are coming in here. It doesn't matter on alpha here, on the prior. So we leave that alpha out here. And it doesn't matter on the capital T. This is the T given W, that's what we are talking about. So it doesn't matter on the data anymore because we got the W fixed. So these are some of the arguments why these conditioning terms are not the same as here. Similarly, W is conditioned exactly on T alpha beta over here. So this equation leads to this. And now we are plugging in, so we know this Gaussian noise model, PFT given X. This says the output of linear regression is T. It is conditioned upon the input X, the weights W, and how is it dependent? And it's a normal distribution. Y of X comma W is the mean, and beta inverse is the variance of that normal distribution. And so we plug in this expression over here, and we plug in the either the Gaussian prior or the Gaussian posterior into it. And if we plug in the Gaussian posterior is what makes sense to plug it in here. That turns out to be this integration that we have, turns out to be a closed form integration. And it takes on, oh, wow, the output is a normal distribution with a certain mean and covariance matrix. And it's in terms of all these things. And this figure over here gives you a sense of what is meant by Bayesian logistic, or this is Bayesian linear regression. It says, this is the same problem we've encountered early on in the course. It's a linear regression problem, and the true data is coming from this green sinusoid here. Let's say I observed one data point, which is this blue data point. What that blue data point is, it's the data generated from this green curve, and some noise has been added to it. So in this case, it's become negative noise over here. To give you one data point and ask you, see, that's the beauty of the Bayesian method. I just give you one sample and ask you to predict in the future for some input what should be the output. The frequentist method will have a lot of trouble with it. A Bayesian method will say, no fear, I have got an idea of the prior distribution of the parameters of this. There's a Gaussian involved here. And this says wherever the sample is occurring, the variance is going to be small for the Gaussian. And as you move away from that data point, a lot of uncertainty shown by this pink region. The pink region gets sharp here around this data point and becomes quite wide. You move away from the data point. And when you have two samples, let's say we got two samples from this data set. Oh, that's good. So you see the pink region now narrows down around these 2 points, and say the output for any, if I give you any input, the output is going to be, somewhere along in this pink region, right? So this is the input is the value of X, and the output is this green value. That's how it should be. But it's going to give you some value in this pink region instead of being on the green curve. Now, let's say we had 25 samples, then we are helping the Bayesian linear regression a lot. It says, oh, you're going to be 25 samples and they're falling all over nicely here. So it says the pink region now is very, very sharp. It says whatever value you're going to give me along this X here, I'm going to tell you the value along this red curve is what I'm predicting it, and with a certain variance associated with it. So this is saying the probability distribution of the output T is normally distributed with a certain mean predicted by the data and a certain variance. So this is what linear regression does. It gives you a range of uncertainty with the data. Okay, and this last line of the slide is an interesting one. It doesn't directly relate to our topic for today, but something to keep in mind is this model, this linear regression model can be interpreted as a kernel method. Kernel method is based on some similarity measure, kxx prime. And x is the input you give me, x prime is a data point. This says if n data points, the output you're going to see, right? The output is some of these over the n samples you got with the kernel function k operating on your sample, your input, and each of the data samples. Tn is the corresponding outputs. And what is this kxx prime? The kxx prime can be shown from these equations to have a form beta times phi of x Sn. It's all the covariance matrix of the data and all that. So it is a very nice expression. So somehow the Bayesian method of linear regression is related to the kernel method of machine learning. So they have a tight relationship between the two. Keep that in mind, because the kernel methods occur again and again in machine learning throughout. They occur in support vector machines, which is a kind of kernel method. They also occur when we discuss variational methods, variational autoencode, and so on. So there is a nice correspondence. Okay. So in Bayesian treatment of logic, so we're not interested in linear regression today. We're interested in logistic regression. We cannot directly integrate over the parameter vector W since posterior is not Gaussian. So you saw there was an integration involved. And we won't have here a Gaussian multiplying a Gaussian inside the integration. We're going to have a Gaussian multiplying a sigmoid. So it is therefore necessary to introduce some form of approximation. Later, we will consider analytical approximation and numerical sampling. So this kind of tells you a little bit about approximation due to intractability. So Bayesian logistic regression, the prediction PCK given X, you understand this problem. We are trying to predict the class given the input. Just this, doing this involves integrating over W. So it says we can write it like this, given the set of outputs also you have, can be written as sigmoid of W transpose phi, that is given set of weights. That's the standard sigmoid output of the classifier. It's 1 or 0, right? We know that much. But it says you need to integrate over all possible values of W, all probabilities. So with W, that's what this PWDW is. It says your output is somehow a summation of the sigmoids for all possible values that W can take. And that's going to be the output. Of course, for some values of W, the probability may be high, and some other values of probability may be 0. If there's 0, then it doesn't contribute anything. And if it is peaked at some point, okay, that's good. It's just that value of sigma right there. It's times. So that peaks there, right? So convolution of sigmoid Gaussian is intractable. You see, this PW, we're going to be assuming Gaussian. Whereas this quantity, which is the main function of the logistic regression problem, is a sigmoid. And we say this is a convolution. When you have two functions like this, at each point we are taking the product and taking the integral over all values. This itself is called convolution, all right? And this convolution is intractable. So it does not have a closed form solution. It is not Gaussian as in linear regression. Linear regression would have a Gaussian or a normal distribution here and normal distribution here. When you multiply by normal and integrate, there is a closed form answer to it. So need to introduce methods of approximation, and the approximations are analytical approximation, which is a Laplace approximation, and the other one is numerical sampling. So the Laplace approximation framework is simple but widely used framework. Oh, wow, it's maybe widely used outside of machine learning, so that's why it's widely used. And it aims to find a Gaussian approximation to a probability density over a set of continuous variables, right? So it is trying to find a Gaussian approximation, that's what we said. Method aims specifically to problems in which the distribution is unimodal. Okay, there is a limitation right there. It says your data is somehow assumed to be unimodal. It doesn't have like peaks, multiple peaks and all that. So that is going to be a drawback with this Laplace. But Laplace is, if you have one peak like the one we saw, then it's a reasonably good method. So consider first the case of single continuous variable. So Laplace approximation 1D case. So this gets into some more interesting mathematics here. We are talking about P of Z or P of Z, right? This yellow distribution here. We're trying to approximate it with a Gaussian, with this red one here. And how do we, so we know P of Z in the sense from the data set, we have figured out that is a distribution, but we need to change it. We need to model it better. So P of Z is going to be replaced by Q of Z. And so we're going to use, so in order to do that, first of all, we need to know the mode of P of Z. Somehow that's not too hard to determine the mode. From your data set, you can figure out what is the most probable value. It can be done numerically, or you can do it as an optimization type of problem and so on. You can figure out what value is it maximum, right? It's a maxima minima type of question for the distribution. To determine Q of Z, we'll use this technique where a probability distribution, let's say P or Q, can be written as 1 over Z phi of Z, where Z is the integral of f of Z dz. So over all possible values, it is integrated over that. And this is some function of Z, need not be a distribution. So it can be some function. And if it is not a distribution, then the sum is not going to be equal to 1. So we need to be integrating over all possible values of that. So that is the denominator here to make sure at every value you're going to get a probability out of it. Right? So P of Z will actually be a probability. Otherwise, it will be some value of some function. So we work with some function and make that into a probability by dividing it by Z, which will force it to lie between 0 and 1. This is, in those of you familiar with probabilistic graphical models will recognize that this looks like what's called as the partition function. All right, it's kind of playing that same role. Okay, value of Z is unknown. If f of Z is a scaled version of P of Z. Goal is to find Gaussian approximation Q of Z, which is centered on the mode of P of Z. First step is to find the mode of P of Z. That is a point Z naught such that P prime of Z naught equal to 0. Oh, that's interesting. It says, if you're trying to find a mode, note that at the mode, the function, the derivative of P is going to be equal to 0. We know that from basic calculus that says at a maximum, the derivative of the function is going to be equal to 0. So we need to solve for P. So we need to find P prime, and then we need to solve for what value of Z is P prime is equal to 0. So that is the value, is we call it Z naught. So that is going to be the mode of this distribution. Okay, now finding the mode is one thing. The other one is what is the nature of the distribution? And we invoke good old Taylor series. All right, it's not so complicated. So let's look at it. A Taylor series expansion of f of x. Supposing I have some function f of x. This says I can expand it out as f of x naught plus f prime of x naught over 1 factorial times x minus x naught plus f double prime of x naught over 2 factorial times x minus x naught whole squared plus this is the third derivative of f of x naught divided by 3 factorial times x minus x naught whole cubed, etc. It's an infinite series. So this thing is a nice workhorse in machine learning, Taylor series. It keeps on getting used, but we never look at the terms beyond for the cube and all that. We just say, we just cut it off saying, let's just use the first 3 terms and simply call this equal as approximately equal. So any function you got can be written like this by these 3 terms. And if you're going to be evaluating this at the mode of any function, then the f prime term is going to be equal to 0, right? So that's where the peak is occurring. So this is 0. It means this middle term here just can be thrown out because it's going to be multiplying by 0. This f prime is going to be 0 at that point when you're evaluating it, that mode. But the second one is called a quadratic term, is x minus x naught whole squared. This quadratic in x. So we take the x into the quadratic. Anyway, some assumption is that f of x is assumed infinitely differentiable at x naught because you're going to be using infinitely differentiable, first order, second order, third order to apply Taylor series. Note that when x naught is the maximum, f prime of x naught equal to 0, and that term disappears when x naught is the maximum. All right, a Gaussian f of x. So we're going to be dealing with f of x that is Gaussian, normal distribution. There's a property that logarithm of f of x is a quadratic function of x. So because the nature of the normal distribution is e to the power of x minus mu whole squared, right? We say that it's a quadratic. when you take a logarithm, the e to the power goes away. So whatever is in the exponent remains, which is a quadratic. And so we're going to be using Taylor series approximation of the function logarithm of f of z and use only the quadratic term. So that's what we're going to do, because we need an approximate version of a quadratic expression, because the original function is quadratic, and we're going to be using a quadratic here also. So finding the mode, of course, we just said it's obtained using numerical optimization. That's p prime of z naught equal to 0. It's the same as d of fz or dz. It's equal to z naught, it's equal to 0. So that has to be done somehow. You have to find the peak. Most of this discussion is about the rest of the problem. Here, it says approximate fz using second derivative. And so logarithm of a Gaussian is quadratic. So we take logarithm of f of z can be written as logarithm of f of z naught minus 1/2 of this quantity here. So this comes about from the Taylor series expansion. Okay, so a is the second derivative of the logarithm of the scale p of z. So we are taking logarithm of the function where a is d squared by dz squared of log fc, right? So that is what is being done here. So all of this, okay, this gives you more detail here. Approximation of f of z, assuming log fz to be quadratic. It is log fc we are replacing. So this expression comes about from the Taylor series expansion, which tells you the second term is missing. No, the first derivative term is missing. Only the first term, and we have this term here. And so log of fc can be written as log of fc naught, and then there is this quadratic term. Taking exponential of this, fz becomes fc naught times exponential of this quantity. And to normalize fc, we need z, which is this integral, and that turns out to have this form. So the normalized version of f of z is q of z equal to 1 over z. We are applying the same rule, 1 over z f of z. So this multiplication gives you this, but that is nothing but normal distribution z given z naught and a inverse. That's the final. So this says, if you give me a unimodal distribution p of z, I'm going to give you a q of z whose mean is at the mode of the distribution you gave me, whose covariance matrix here is in terms of this A inverse. And what is that A inverse? A itself is the second derivative. And it's saying A inverse is 1 over that quantity, or the inverse if it is a multivariate case. So that is what Laplacian does. It's a very simple approach to finding a Gaussian distribution whose modes correspond. So this diagram shows some of this. Let's see, this particular distribution, this yellow distribution, it happens to be, has this form. P of z is proportional to exponential minus z squared over 2 sigma. Okay, this is actually a sigmoid multiplied by a Gaussian function here, proportional to that. And that's what this function looks like. And the Laplace approximation is this red one. And they're showing here the negative logarithm of these quantities over here. And so for each value of z, the negative logarithm of this yellow one kind of goes like this and like that. And the red one corresponds to the nice Gaussian here. So negative logarithm looks like this. And so this was the fz, and the qz QZ is normal distribution Z with Z naught. So we just saw that kind of a thing here. And Gaussian approximation will only be well defined if its precision A greater than 0 or the second derivative of fz at point z naught is negative. So there are some restrictions on the nature of the A. This slide will skip on Laplace's method again or some case. So Laplace approximation in m dimensions is approximate pz equal to fz over z defined over m dimensional space. And so now A becomes an m by m Hessian matrix. So I think we went over Hessian earlier on, right? And I don't know if we did it last class or earlier on. Hessian is the second derivatives arranged in the form of a matrix. And we are talking about the matrix involves ith variable, jth variable, and so on. So you have these second derivatives, partial derivatives that form a matrix. It's an m by m. M is a feature space size, and A is of that form. And now we have f of z has this form, and z, the denominator, is going to have this form. So the distribution q of z is proportional to f of z, as q of z is equal to n z. Oh, this looks exactly the same as the one-dimensional case. That this is going to be nothing but peaked at the distribution, and you have to find the covariance matrix, find the second derivative matrix, and invert that, and that's what's going to be a covariance matrix. So steps in applying Laplace approximation. Find the mode Z naught using a numerical optimization algorithm. Evaluate Hessian matrix A at that mode. There are all kinds of routines to find Hessian matrix of a given distribution. But many distributions encountered in practice are multimodal. There will be a different approximation according to which mode is considered. Z of the two distribution need to be known to apply Laplace method. All right, so we saw some methods of determining the Z. So what are the weaknesses of Laplace approximation? Directly applicable only to real variables based on Gaussian distributions. So it is based on the Gaussian distribution to real variables. And the method is based on Gaussian, rather than the data is based on Gaussian. May be applicable to a transformed variable. All right, so some issue about, so that sounds like a strength rather than a weakness, right? Yeah. Based purely on a specific value of the variable. And variational methods have a more global perspective. So the Laplace method is a first cut approximation. If you're going to be using a variational method, a baseline would be, how much better is it than if you had used Laplace? And then comes approximating Z. It says the Z value we saw earlier on is written like this. As well as approximating the distribution P of Z, we can also obtain an approximation to the normalizing constant Z. Z is equal to integral of f of z, and that's approximately written using the quadratic expansion like this. And so one can figure out the Z here. Can use this result to obtain an approximation to model evidence that plays a central role in Bayesian model comparison. This particular equation, by taking the logarithm and all that, gives an interesting expression for model comparison. So what is model comparison? So bear with me while we are still doing something on Laplacian. We are kind of changing mode in this slide, and we come back to the previous one. Let's consider a data set D and models Mi having parameters theta I. So we have a problem with several models. I mean, this sounds like a very general problem. I'm trying to solve this problem. There is a given data set D, and I have these models for this problem M1, M2, M3. Each of them has their own parameters theta I. So this is like I have a neural network solution to this problem, and then I have a deep neural network solution to this problem, and another deeper neural network solution to the problem. I want to compare them. And to compare them, and you have a given data set D. So we have all these models MI lined up, and they all have these parameters. And this says for each model, define the likelihood P of D given theta I MI. Oh, okay. This says, what is the probability distribution that is assigned to the data that you have? And so it's going to evaluate it. The model that is best is the one that gives the highest probability to the data set that you have. All right. So this is like a likelihood. This is what likelihood is about. Probability of the data given the model and its parameters. Right. So what is the likelihood? You remember that all of machine learning is about maximizing the likelihood, and that's how we choose the parameters. And this says, okay, fine, you maximize the likelihood and you've got the parameters. Okay, what is the probability it assigns to some given data set D? And it says introduce prior theta I given mi over the parameters. Oh, okay, so for that model, the parameters that it has is a Bayesian, right? It's got a distribution over it, right? So any prediction we're going to make is going to be integrated over all the values of these. So we need model evidence. This is called model evidence for various models, P of D given M sub I. So let's just now, instead of working with many models, let's just work with one model, and then that's going to apply to every one of the models. So for a given model from some rule of probability, so each model assigns a probability to the data. Probability of D is equal to probability of D given theta times P theta D theta. So this assumes a prior distribution to the parameters. So we are integrating out the parameters in this sum rule. And identifying f theta is equal to P of D given theta times P of theta. We are calling this as f of theta here. And z equal to P of D. And using, all right, using z is equal to, we had seen this expression earlier on. So log P of D can be written as a log of integral f of theta d theta. Okay, so this is an integral of this over these parameters here. And plugging in that value here, f of theta is a definition. It is this quantity actually. And we are now obtaining logarithm of f of theta. The maximum a posteriori, we are choosing the one value of theta, the maximum a posteriori probability value of theta, and the rest of this expression here. And so that gives probability the data is going to have this complicated looking thing, but a lot of this is not dependent on the data here. And it becomes a factor that penalizes model complexity, where theta map is the value of theta at the mode of the posterior, and A is the Hessian of the second derivative is the negative log posterior. This looks pretty complicated, but the next slide shows that all of this gets very simplified in this way. Assuming a broad Gaussian prior over parameters and Hessian is a full rank, approximate model evidence is log P of D is equal to log P of D given theta map minus 1/2 m log n. This is saying, so we are now evaluating one model. And it says the log probability assigned to a data by the model is given by the probability assigned to the model by the value of the parameters that is most likely. And then there is an interesting term, 1/2 mn log n. M is the number of features that you're dealing with. N is the number of data points that you have. N is the number of data points. M is the number of parameters in theta. This is a very popular measure of clustering. So you have an unsupervised learning problem and you're figuring out how good is my clustering result. And if you want to say how many clusters are there, so you can do it for 3 clusters, 4 clusters, so on. And in that case, this M reduces to the number of clusters and N is the number of data points there is. And what is the probability assigned to the data by particular clustering? And so that is evaluatable. Given a set of data points, you can always figure out the probability assigned to that particular data. And so this term comes into play. So when you're evaluating the goodness of a clustering method, you can evaluate this quantity, which is referred to as the Bayes information criterion, or the BIC. So you would evaluate BIC for each model and see as to which model assigns the highest probability to the data, whether it's divided by three clusters or 4 clusters or 5 clusters and so on. You can compare. There's another measure called AIC, given by log probability of data given WML minus M. And BIC penalizes model complexity more heavily. All right, so there is AIC, BIC, or methods. Some weaknesses are there, sure, So Bayesian approach to logistic regression is more complex than for linear regression. Predictive distribution needs an integral over the parameters. And Laplace approximation fits the best Gaussian. And normalization term is useful, okay. All right, so this is a bit complicated, all right. But I just wanted you to have a flavor for it. And the lesson you get out of it is the logistic regression involves something more complicated, not just because we're dealing with a prior and posterior of the parameters, but also we have to worry about how do you combine the distribution of the parameters with the distribution assigned by the model itself, right? So those two have to be taken into account. All right, now let's close this one. Mihir, how are we doing on time?
We can start the breakout sessions now.
Oh, you're ready, huh? Okay. I had 3 lecture slides for today, so of which we finished only 1. So I guess we'll have to go over one more session of this kind of a. Some semesters when I teach machine learning, I've completely skipped the Bayesian approach and says, okay, this is too complicated. The students are going to get lost in this, and let's go on to the next topic. But you see, it's actually a very intriguing topic. That's why I kind of motivated you with the mountain climbing and all that, saying some of you may actually end up being serious researchers in machine learning. And Bayesian machine learning is a rich topic to explore. But for that, you need to get your fundamentals right. This is the nature of it. So we just started with the Laplace approximation. And then we go on to a little bit more detail about the Bayesian logistic regression. And then other than Laplace, we go on to the variational approach also. So we'll try and do both next time, okay? And Mihir, I'll let you take over at this point.